P-block elements are one of the most important sections of the modern periodic table. The term p-block refers to those elements in which the differentiating or last added electron enters a p-orbital of the valence shell. In the modern periodic table, the p-block occupies the right-hand side and consists mainly of groups 13 to 18. These 6 groups are called the p-block because a p-subshell contains 3 orbitals, and each orbital can accommodate a maximum of 2 electrons. Therefore, a completely filled p-subshell can contain a maximum of 6 electrons. This is why the p-block contains exactly 6 groups, corresponding to the possible arrangements of 1 to 6 electrons in the p-subshell. To understand the p-block properly, first remember the basic idea of electronic configuration. Electrons are arranged around the nucleus in different shells and subshells. The main subshells are S, P, D, and F. The S subshell has 1 orbital and can hold a maximum of 2 electrons. The P subshell has 3 orbitals and can hold a maximum of 6 electrons. The D subshell has 5 orbitals and can hold 10 electrons, while the F subshell has 7 orbitals and can hold 14 electrons. In p-block elements, the important point is that the final electron responsible for differentiating one element from the previous element enters a p subshell. The 3 p orbitals are conventionally represented as px, py, and pz. These 3 orbitals have the same general dumbbell shape but are oriented in different directions in space. The px orbital is oriented along the x-axis, the py orbital along the y-axis, and the pz orbital along the z-axis. Since each orbital can accommodate 2 electrons with opposite spins, the total capacity of the p subshell is 6 electrons. This simple fact is extremely important because it explains why the p-block extends across 6 groups, from group 13 to group 18. The general valence shell electronic configuration of p-block elements is written as NS2, NP1 to NP6. Here, N represents the principal quantum number or the outermost shell. The S subshell contains 2 electrons, while the P subshell contains between 1 and 6 electrons depending on the group. For group 13, the general configuration is NS2, NP1. For group 14, it is NS2, NP2. For group 15, it is NS2, NP3. For group 16, it is NS2, NP4. For group 17, it is NS2, NP5. Finally, for group 18, the general configuration is NS2, NP6. This gradual increase from 1 p electron to 6 p electrons explains the arrangement of the 6 p-block groups. There is an important exception that students should remember. Helium is placed in group 18 because it is a noble gas and has a completely filled outer shell, but its actual electronic configuration is 1s2, not 1s2, 1p6. Therefore, helium does not have its differentiating electron entering a p orbital. From the point of view of electronic configuration, helium belongs to the s block, but because of its chemical properties and completely filled shell, it is positioned with the noble gases in group 18. This is a very important examination point. The p block begins with group 13, known as the Boron family or boron group. The members are boron, aluminium, gallium, indium, thallium, and nihonium. Their general valence configuration is NS2, NP1. This means that these elements have 3 valence electrons in total. Boron is a metalloid, while the heavier members show increasingly metallic character. Aluminium is an important metal, and gallium, indium, thallium, and nihonium are also classified as metals. The common oxidation state of this group is +3, especially for the lighter members, although the stability of the +1 oxidation state increases down the group because of the inert pair effect. Group 14 is called the carbon family or carbon group. Its members are carbon, silicon, germanium, tin, lead, and flerovium. The general valence configuration is NS2, NP2. giving 4 valence electrons. Carbon is a nonmetal, silicon and germanium are metalloids, while tin and lead are metals. This group is particularly important because carbon forms an enormous number of compounds. Carbon also shows strong catenation, meaning that carbon atoms can bond with one another to form long chains, branched structures, and rings. The common oxidation states include +4 and +2. And the stability of the +2 state increases down the group because of the inert pair effect. Group 15 is known as the nitrogen family, or pnictogen family. Its members are nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. The general valence shell configuration is ns2, np3. Therefore, these elements have 5 valence electrons. Nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, while bismuth and moscovium are metals. Nitrogen is extremely important because it is a major component of the atmosphere and is also present in proteins, nucleic acids, and many fertilizers. The common oxidation states of group 15 elements include -3, +3, and +5, although their stability varies as we move down the group. Group 16 is called the oxygen family or chalcogen family. Its members are oxygen, sulfur, selenium, tellurium, polonium, and livermorium. Their general valence configuration is ns2, np4. These elements have 6 valence electrons, so they need 2 additional electrons to achieve a stable noble gas-like configuration. Oxygen and sulfur are nonmetals, selenium is also a nonmetal, tellurium is a metalloid, while polonium and livermorium are metals. The common oxidation state is -2, especially for oxygen, although heavier members can show positive oxidation states such as +4 and +6. Group 17 is known as the halogen family. Its members are fluorine, chlorine, bromine, iodine, astatine, and tennessine. Their general valence configuration is ns2, np5. Therefore, halogens have 7 valence electrons and need only 1 additional electron to complete their outer p-subshell. Because of this electronic configuration, halogens are highly reactive elements and readily form -1 ions. Fluorine is the most electronegative element in the periodic table. Chlorine and bromine are also highly reactive nonmetals. While the heavier members show increasing metallic characteristics, halogens commonly form salts with metals, which is why the term halogen means salt former. Group 18 is known as the noble gas family. Its members are helium, neon, argon, krypton, xenon, radon, and oganesson. Except for helium, the general valence configuration is ns2, np6. This represents a completely filled valence shell. Because their outer electron shells are highly stable, noble gases generally have very low chemical reactivity compared with most other elements. Helium has the configuration 1s2, while the other noble gases have completely filled S and P subshells in their outermost shells. Although noble gases are generally unreactive, some heavier noble gases, particularly xenon, are capable of forming compounds under suitable conditions. One of the most important features of the p-block is that it contains elements with very different properties. Unlike the s-block, which mainly contains metals, the p-block contains nonmetals, metalloids, and metals. For example, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, and the noble gases are nonmetals. Boron, silicon, germanium, arsenic, antimony, and tellurium are generally classified as metalloids. Aluminium, gallium, indium, thallium, tin, lead, bismuth, and several heavier p-block elements are metals. Therefore, the p-block shows a very wide range of physical and chemical properties. The p-block also contains many elements that are essential for life. Carbon is the fundamental element of organic chemistry and is present in carbohydrates, proteins, fats, nucleic acids, and countless other compounds. Hydrogen and oxygen are major components of water. Nitrogen is essential for proteins and DNA. Phosphorus is important in DNA, RNA, and energy transfer molecules, and sulfur occurs in important biological compounds. Chlorine is involved in biological processes and is also widely used for water treatment, while many noble gases have applications in lighting, electronics, and specialized industrial processes. The position of the p block on the periodic table can be understood very easily. The periodic table is divided into 4 major blocks according to the subshell receiving the differentiating electron. The S block is on the left side and mainly contains groups 1 and 2. The D block occupies the central region and contains groups 3 to 12. The P block is on the right side and contains groups 13 to 18. The F block is usually displayed separately at the bottom and contains the lanthanides and actinides. Therefore, when looking at a modern periodic table, the P block can immediately be recognized as the large 6-column region on the right side. Across a P block period, the number of P electrons gradually increases from 1 to 6. For example, in period 2, boron has the valence configuration 2s2, 2p1. Carbon has 2s2, 2p2. Nitrogen has 2s2, 2p3. Oxygen has 2s2, 2p4. Fluorine has 2s2, 2p5, and neon has 2s2, 2p6. This sequence demonstrates the basic structure of the P block very clearly. The same general pattern occurs in the higher periods, although additional inner electron shells are present. The electronic configuration also explains many periodic trends in the P block. As we move from left to right across a period, the nuclear charge increases while electrons are added to the same principal shell. The effective nuclear charge generally increases, causing atomic radius to decrease across the period. At the same time, ionization energy generally increases, electronegativity generally increases, and metallic character generally decreases. Therefore, the left side of the P block contains more metallic elements, while the right side becomes increasingly non-metallic and finally ends with the noble gases. When we move down a P block group, additional electron shells are added. As a result, atomic size generally increases, shielding effect increases, and the attraction between the nucleus and the outermost electrons becomes weaker. Ionization energy generally decreases down a group, while metallic character generally increases. However, P-block elements show several important irregularities and exceptions, so periodic trends should always be understood rather than memorized blindly. Another major feature of P-block elements is variable oxidation states. The number of valence electrons changes from 3 in group 13 to 8 in group 18, so different elements can participate in bonding in different ways. The heavier P-block elements also show the inert pair effect. The inert pair effect refers to the increasing tendency of the outermost s-electron pair to remain relatively less involved in bonding as we move down certain P-block groups. Because of this effect, lower oxidation states become increasingly stable for heavier elements. For example, in group 14, the +2 oxidation state becomes more stable as we move from carbon toward lead. Similarly, in group 13, the +1 oxidation state becomes more stable for heavier elements. P-block elements form an enormous variety of compounds. They can form ionic compounds, covalent compounds, molecular compounds, network solids, acids, bases, oxides, hydrides, halides, and many complex compounds. Nonmetals of the P-block generally form covalent bonds because their electronegativities are relatively high. Metals in the P-block can form ionic or metallic compounds. This tremendous variety is one of the reasons P-block chemistry is considered one of the largest and most important parts of inorganic chemistry. The P-block also plays an important role in the study of oxides. Across a period, the nature of oxides generally changes from basic to amphoteric and then to acidic as metallic character decreases. For example, in period 3, sodium and magnesium form mainly basic oxides, aluminium oxide is amphoteric, silicon forms a weakly acidic oxide, and the oxides of phosphorus, sulfur, and chlorine are increasingly acidic. This change is directly connected to the gradual decrease in metallic character across the period. Another important characteristic of p-block elements is the presence of allotropy in several elements. Allotropy means that an element can exist in different structural forms in the same physical state. Carbon, for example, exists in forms such as diamond and graphite, which have very different properties despite being made entirely of carbon atoms. Oxygen exists mainly as molecular oxygen, O, and also as ozone, O. Phosphorus and sulfur also show different allotropes. These differences arise from different arrangements and bonding patterns of the same type of atoms. The p-block is also extremely important for industrial chemistry. Nitrogen is used in ammonia production and fertilizers. Oxygen is essential in medical applications, combustion, and industrial processes. Chlorine is widely used in water purification and chemical manufacturing. Silicon is essential in semiconductor technology and modern electronics. Aluminium is used extensively in transportation, construction, packaging, and electrical applications. Carbon-based materials are fundamental to fuels, polymers, pharmaceuticals, and biological chemistry. Noble gases such as helium, neon, argon, and xenon also have specialized applications in cooling, lighting, welding, electronics, and scientific equipment. For examination purposes, the easiest way to remember the structure of the p-block is to connect each group with its number of p electrons. Group 13 has NP1, Group 14 has NP2, Group 15 has NP3, Group 16 has NP4, Group 17 has NP5, and Group 18 has NP6. Therefore, as we move from Group 13 to Group 18, the number of p electrons increases one by one until the p-subshell becomes completely filled. This is the fundamental reason why the p-block consists of 6 groups. So, the complete concept can be summarized naturally like this. P-block elements are the elements of the right side of the modern periodic table in which the differentiating electron enters a p-subshell. They occupy groups 13 to 18 and therefore contain 6 groups. The p-subshell consists of 3 orbitals, px, py, and pz, and each orbital can hold 2 electrons, giving the p-subshell a maximum capacity of 6 electrons. The general valence shell configuration of the p-block is ns2, np1 to np6. Group 13 is the boron family, Group 14 is the carbon family. Group 15 is the nitrogen family, Group 16 is the oxygen or chalcogen family, Group 17 is the halogen family, and Group 18 is the noble gas family. The p-block is especially important because it contains metals, metalloids, non-metals, and noble gases, and therefore shows an enormous variety of chemical behavior. Understanding its electronic configuration provides the foundation for understanding its periodic trends, oxidation states, bonding, reactivity, compounds, and practical applications.